Hello, 5th graders, and welcome to a read-aloud of today's science ebook. That's this one here, titled Changing Matter, Understanding Physical and Chemical Changes, as needed for today's science lesson, Unit 2, Lesson 15, titled Changes in Matter. So for today's science ebook, we'll be reading pages 4 through 21, which is basically going to be the whole thing. And as we read today's ebook, we'll be seeing all about the different ways that matter can change in our universe, whether it be from changing from solid, liquid to gas, or perhaps changing into completely different substances one to another. So with that said, going straight into the ebook today. Going straight to starting on here on page 4, 2 ways to change. Everything is matter. It's made of something and takes up space. Matter changes in 2 ways: physical changes and chemical changes. Let's look at the differences. Physical changes create different states or forms of the same matter. Water is still water if it changes from a liquid state into ice, which is a solid state. So liquid water, solid ice, and even water vapor. There may be 3 different phases, solid, liquid, and gas, but they are still water. Those molecules are still water molecules. Chemical changes create entirely new substances. After the chemical change, physical methods such as cutting, drying, filtering, spinning, or changing temperature or pressure can't undo the change. Spellbinding alchemy. Ancient scholars called alchemists believed they could change metals into gold or produce other amazing results. Modern science has never proven their claims. However, their quests have inspired many stories, including Harry Potter and the Sorcerer's Stone. So it is interesting to see how science has come such a long way. Now here's another example of a chemical change, wood being set on fire to create ash. Fire chemically changes wood into a new substance, ash or soot and gas. You can't bring the wood back after it is burned. So that would be an example of a chemical change. Wood being turned into a completely new substance as a result of being exposed to the heat and energy of fire. Next up, physical changes. All matter is made of tiny moving particles called molecules. They move slower or faster in different states, such as solids, liquids, or gases. So an example of a solid, like a hard candy right there, a solid has a shape because its packed molecules move very slowly. So all the molecules inside that piece of candy right there are packed together really tight, and they're barely moving at all, therefore making them a solid. Looking at a liquid though, like this tomato soup right here, a liquid takes the shape of its container. Liquid molecules have room to flow under and over each other. So if you were to zoom in on the molecules that make up that soup, you'd see that the molecules are not as tightly packed as they are in the solid. There's a little more room in between them. They're able to kind of flow in and around each other. Therefore, that makes a liquid able to flow around the way it does. A gas completely fills the shape of its container. Its fast-moving molecules have a lot of space between them and bounce off the container's walls. Gas molecules in air fill all of the space inside of a balloon. So inside of that balloon there is probably helium gas. So all the little helium atoms are bouncing around really, really high speed inside that balloon with a lot of space in between them. Moving on, physical properties help identify a substance and how it changes. When does it boil or melt? Is it magnetic? Does it dissolve in water, like sugar or salt? Density is a physical property that describes how packed or how concentrated a substance is. A crumpled paper ball has less density than a rock of the same size. So if the substance crushes easily like the paper, like a paper ball, it has low density. But if it resists crushing, like a rock, then it has high density. So that crumpled up paper ball and that rock right there, they may be the same size, but if you were to hold each one in both of your hands, the rock would certainly feel a lot heavier. Furthermore, it would also be a lot harder to squeeze that rock smaller, right? You could probably squeeze that paper ball into a smaller size, but the rock would resist being crushed. That's a sign that the rock has a lot more matter packed into it, and it's much more packed closely together when compared to the molecules that make up the piece of paper. Very low density for the paper, very high density for the rock. Another physical property, viscosity, is a physical property that refers to how easily a liquid flows. So if a liquid is runny, like water or juice or milk, then it has very low viscosity. It flows very easily. But if it's gooey, like honey, then it has a high viscosity. So honey being kind of thick and sticky and doesn't run very easily would have a high viscosity. Some other things that might have it are like, I think of like tar or ketchup or mustard. Very high viscosity liquids, those would be. Another very important law we have here, we have the law of conservation of mass. All matter keeps its mass, which is the amount of itself or the amount of particles it has, even after a physical change. For example, the steam's mass equals the mass of the original liquid's mass. So if you have a bunch of water in a kettle and then you heat it up so that it becomes steam, the total mass of the steam is going to be equal to the amount of water that was originally in the kettle. Furthermore, if you have a bunch of liquid water and you freeze it into ice, you're going to have the same amount of ice in the liquid water as the same amount of molecules, water molecules in the ice as you would have had in the liquid water. Next up, chemical changes. Chemical changes happen everywhere. In a chemical change, tiny atoms inside different materials' molecules rearrange and share their structures. This new molecular bond forms an entirely new substance, which is called a compound. So did you know that photosynthesis is a chemical change? That being the process by which plants absorb energy from the sun and turn it into energy they can use. The green chlorophyll in plants uses the sun's energy to make food called sugars from water and carbon dioxide. So really powerful example of a chemical change happening there. Plants using the power of the sun and essentially turning it into sugar. So what we have here is an example of the formation of a compound. If you have one carbon atom that happens to come into contact with two oxygen atoms, they will actually form a compound that we call carbon dioxide. So the carbon atom will bond with the two oxygen atoms like so, forming a carbon dioxide molecule. That's another example of a chemical change. So any change that results in atoms bonding together to form new molecules, or perhaps even molecules breaking apart into their individual atoms, that would be an example of a chemical change. Speaking of atoms, in each atom, the protons that carry a positive charge and the electrons carry a negative charge. The number of particles in an atom makes the atomic weight. Millions of atoms could fit in this period. Yes, atoms are very, very tiny indeed. Some atoms easily make new compounds. These reactive atoms, such as hydrogen and oxygen, have charged particles that look for others to bond with to create an electrical balance. Some atoms bond in other ways too. Bonding allows atoms to balance their charges or fill spaces in their outer shells. They combine to form a very important molecule on Earth called water. So there's another example of a common molecule I'm sure we've seen before. If a single oxygen atom happens to run across two hydrogen atoms, they will bond together and form a molecule of water. H2O, two hydrogens and one oxygen. In fact, that's mentioned right here. Have you ever heard someone call water H2O? H2O is the chemical name for water. It means two hydrogen atoms and one oxygen atom. So some other chemicals that are the result of different types of atoms bonding together to create new molecules that you may be familiar with. If an atom of sodium bonds with an atom of chlorine, that will actually create sodium chloride or table salt, like the salt you put on your food. Sugar is a combination of carbon, hydrogen, and oxygen. And baking soda is sodium, hydrogen, oxygen, and carbon. So here's a neat example of a reaction we may have seen before. Neon, which is a noble gas used to make bright lights, is non-reactive. Neon atoms have the maximum number of electrons they can hold in their outer shell. Because missing electrons in the outer shell is what makes elements reactive, neon can't combine easily with other atoms. So on that note, not all atoms invite chemical change. Gases such as neon, which is the gas that's used to make those cool looking neon signs, Helium and argon have stable electrical charges and do not usually make chemical compounds. They are called the noble gases. The potential for an atom to change into a new chemical is an important property for researchers to know before they experiment. Oxygen changes easily and can produce fast results, maybe even an explosion. Yes, oxygen, unlike neon or argon, oxygen is highly reactive. It has some empty spaces in its outer shell that it makes it very, very quick to bond with other atoms that can produce pretty devastating results if it mixes with certain substances. Nothing burns without oxygen. But some materials, such as hydrogen, diesel fuel, or lithium metal, mixed with pure oxygen and heat, burn so fast that they appear to explode. Indeed, they do. So pure oxygen is actually quite deadly for that reason. Some chemical changes happen where you can plainly see them. A campfire leaves ashes behind, for example. Other chemical changes seem invisible, such as digestion inside your body. Like when you eat food and your stomach digests it up. That's an example of a chemical change as well. Some chemical changes happen quickly. Vinegar and baking soda mixes into an explosion of bubbly carbon dioxide. If you've ever seen one of those volcanoes before, that's made of a mixture of baking soda and carbon dioxide. Baking soda and vinegar, which releases a bunch of carbon dioxide gas. You could maybe even make bottle rockets out of that too. Other chemical changes happen much more slowly. How they change depends a lot on the chemicals involved. So an example of a very slow-acting chemical change would be a piece of metal rusting over many weeks or months if it's left out in the sun and left out exposed to the elements. This chemical reaction made by combining vinegar and baking soda is actually two reactions happening very closely together. The acid in vinegar reacts with the baking soda to form an unstable, mild acid. This acid breaks down right away into carbon dioxide and water. The bubbles come from the escaping carbon dioxide gas. So all those bubbles you're seeing from that reaction are full of carbon dioxide. The carbon dioxide is heavier than the air, so it flows over the jar. Changing fact. Chemical changes can occur slowly over time. Oxidation, or rusting, changes hard iron into crumbly dust when the oxygen in the air combines with the metal. Molecules at work. Wallace Hume Carothers, an American chemist, experimented with long chains of molecules called polymers in the 1930s. His work led to nylon, which is used in a lot of clothing and things like backpacks. In 1940, shoppers bought more than 60 million pairs of nylon stockings. Since then, countless products have used nylon, from toothbrushes to military parachutes. Your backpack is most likely made of nylon. What else will you use today made of nylon? Might be something worth looking up. Today, researchers use the scientific method to find new ways of combining matter and its molecules. Scientists ask questions and compare their answers to what's already known. They share their results. Other scientists test the ideas following the same steps. So we've looked at the scientific method before, but it's worth repeating here because it is really used all the time in science. Step 1 is to ask a question. Step 2 is to conduct some background research to see what's already known about your question. Step 3 is to form a new idea to test. So, in other words, make a hypothesis. 4, test the idea with an experiment that can be repeated by other people. 5, draw a conclusion. So decide what you might learn from your experiment. And 6, report the results so that other people can see what you found out. If an idea doesn't work out, start again at step 3, forming a new idea to test. Good or bad chemical changes? In the past 300 years or so, scientists have created medicine, clothing, food, building products, and many other useful materials. I think we would all agree that those are very good things that have been done using chemical changes. But creating chemical changes can also bring pollution, poison, and other destructive results. For example, acid rain looks like clean rain, but it can kill fish, stunt tree growth, and spark asthma attacks. So that right there would be a picture of a forest that was under the influence of acid rain, which would be raindrops that are highly acidic. Factories that burn coal, for example, release chemicals that react with water, oxygen, and other gases high in the atmosphere that make acid rain. With more research, scientists will continue to learn more about changing matter. As they learn more, they will find new ways to help us and our planet. Indeed, we want to try to use our knowledge of chemistry and the changing states of matter to try to help the world as much as possible and try to avoid destruction like this. And with that, everybody, that will conclude our Read Aloud of today's science ebook. Hope you found it interesting today, and hopefully you'll take that knowledge with you into your science lesson. So go ahead and complete the rest of it, and we'll see you next time. Take care, everybody. Have a good day.